Hello again. This is Math 2-115 coming to you from the College of DuPage, and the title of this lecture is Sequences, Strings, and Such. Remember, you are controlling the throttle and the transmission of this presentation. A sequence S is a function whose domain D is a subset of integers. The notation S sub n is typically used instead of the more general function notation S of n. The term n is called the index of the sequence. If D is a finite set, we call S a finite sequence, otherwise it is an infinite sequence. A sequence S is denoted S, or in brackets S sub n, if n is the index of the sequence. If, for example, the domain is a set of positive integers z plus, S or bracket S sub n denotes the entire sequence, S1, S2, S3, ... and so on, never ending. We use the notation S sub n to denote the single element of the sequence S at index n. In this book, we will frequently use either the positive integers or the non-negative integers as the domain of a sequence. If the domain of a sequence is the infinite set of consecutive integers, k, k plus 1, k plus 2, and so on and so forth, the index and the index of S is n, we denote this as, and you see that we're starting at n equal k and going up to infinity. Two important types of sequences are increasing sequences and decreasing sequences, and non-increasing and non-decreasing. So the definitions follow, and they look rather stilted, but they're actually kind of simple. And a sequence is increasing if each subsequent element is larger than the one before, and decreasing and non-increasing and non-decreasing kind of mean the same sort of thing, except it does allow the subsequent terms to be equal. One way to form a new sequence from a given sequence is to retain only certain terms of the original sequence, maintaining the order of terms in the given sequence. The resulting sequence is called a subsequence of the original sequence, and here is a formal definition. So if you have S as a sequence, a subsequence of S is a sequence obtained from S by choosing certain terms in S in the same order in which they appear in S. Order does matter. So the notation for subsequences then is going to be this. This is S sub n k. And you see n1, n2, n3 denote the indices in order of S of the terms that are selected to obtain the subsequence. You want to think about this a little bit, particularly in addressing some of the problems. Now we do operations on sequences, and in fact, when we have a sequence, we define a sequence on top of the sequence. So if this is a sequence, a sub I running from I equal m to n, then you can define the summation of the a sub i's going from m to n to be, what you do is you start with this index, you plug it in until you get am. This sigma notation means add, plus, then you go to the next one, you increment the index, so this is n plus 1, plus ... and you go all the way up to a sub n. This is the summation. You can do the same thing with products. When you take this, you're just multiplying all of these numbers together, all the way through m through n, and they're a sub m and a sub n is what is multiplied together. And this notation is called the sum, or sigma notation. That's a Greek sigma. And this is called the product notation, and that looks like a capital pi. I is the index, m is the lower limit, and n is called the upper limit. Okay, let's practice a little bit these with problems. So we have the sequence a sub a sub n and b sub n, but we're defining these by an explicit formula. So a sub k is equal to k over k plus 1. And b sub I is equal to I minus 1 over I. And you see this k and the i's are indices, but they're dummy variables. Any letter could be used. This one is for every k bigger than or equal to 1. This is for every integer bigger than or equal to 2. Compute the first 5 terms of both sequences. Okay, so what you're going to do is you're going to plug 1 in, and this is A1. So A1 is 1/2. A2 is 2/3. A3 is 3/4. A4 is 4 over 5. A5 is 5 over 6. B2, and you see B starts with 2. The sequence B starts with 2. So B2 is 1/2, 2/3, 3/4, 4/5, and 5 over 6. Now if you look at these both actually define the same sequence, but their definitions look different. That can certainly happen. Let's look at another example here. This is called an alternating sequence. So the first 6 terms, this one starts at 0, C1, C2, or C0, C1, C2, and it's defined this way. Cj, for every integer j bigger than or equal to 0, is minus 1 to the j. So when you go through, what you find is that this bounces back and forth between 1 and minus 1, depending on the parity of the exponent, and remembering that minus 1 to the 0 is 1. So that's the sequence, and this is called an alternating sequence because it alternates with SIG in S's. Sometimes the problem will be the other way about. We will give you a sequence and you're supposed to find an explicit formula that will have the following initial terms. And again, there's not always a unique answer. In this case, you have 6 terms, and the answer could be anything as long as it gives these first 6 terms, because you really don't know what happens in this dot, dot, dot. So anyway, this is given the initial terms, finding the explicit formula. So you start looking at these and trying to say, well, okay, so what's going on? And this is not trial and error, but it is careful and critical thought process. And what you learn here then is you say, well, okay, I can kind of see what this might be. And in fact, I'm jumping all the way to the end here. But what we can see is that in order to get the SIGN right, we have to take this minus 1 raised to the k plus 1 over k squared. And that is going to fit this, this formula. By the way, what you should realize is, oh, there are multiple correct formulas. This one would also be correct, because all we've done is shift the index. So again, reminding you it is possible for 2 sequences to start out with the same initial values but diverge later on. And okay, let's continue. And here we're computing some summations. So we know that A1, A2, A3, A4, and A5 are these numbers. So you're to compute, what is it when I sum from 1 to 5, from 2 to 2, or from 1 to 2? Well, I really am just letting this work. This adds A going from K rather, going from 1 through 5, put them in, and substitute the values and add them, and I get 0. Now here, there is no increment, so K is equal to 2, and then we're done because we stop at 2. That's just going to be minus 1, and here we go, minus 1. Oh wait, here is an important thing. This is a subsequence. This is A2K. So that means we're only taking the even values of the sequence. So this is going to be when K is equal to 1, that is going to be 2. When K is equal to 2, that's going to be 4. So I calculate that, and I will get 0 for that. Oftentimes, the terms of a summation are expressed using an explicit formula. For instance, it's common to see summations such as the summation k equal 1 to 5 of k squared, or the summation from I equal 0 to 8 of minus 1 to the I, all divided by I plus 1. We'll continue this discussion in 14.1. See you there.